Hello everyone. Thank you for attending our talk. I'm David Sommer.
And I'm Aditya. We are from ETH Zurich, and today we're going to present our talk, Cover Up, a way to provide deniable upload and download channel that provides really nice deniable guarantee.
So Aritra, let me ask you a question. Were you ever afraid to download something that's easily accessible? You know, maybe someone is watching.
That's an interesting question. So a few days back, I was actually visiting WikiLeaks to get some leaked document. But by the evening, I was actually left with a broken arm, as you can see. And I'm pretty sure these two events are completely uncorrelated.
Come on, please be serious. This is an important topic, for example, for whistleblowers, free speech, and journalists should, in general, accessing primary sources. This is important for informed democracy.
Exactly, but why not we stick to very well-known construct like anonymous communication networks or ACNs? So there is already well-known ACNs such as Tor, I2C, Freenet, all of them are available freely for download. ACN provides variable means to remove the connectivity between the sender and receiver. So your ISP or government doesn't actually know that which websites you are visiting. So they're actually pretty good to limit surveillance and censorship up to a certain limit. So why not just stick to ACN?
There are two fundamental problems with ACNs. First, when you connect to them, your ISP or maybe a government agency can see when they look at the network traffic that you're actually connecting. So this is already suspicious, and this might suck depending on your situation and gives you little deniability. Second problem is the bootstrapping problem. Assume you have an ACN with unattractive latency, for example. That means there are a low number of connected users. This means small anonymity sets, which then leads to an unattractive degree of anonymity again. So new users will not really be motivated to join the network.
Exactly. So ACNs are pretty great, but they have actually some pressing issues. So which is why we decided not to pursue ACN, but we have our own idea. We are calling it passive participation. Now, what is this idea of passive participation? It's basically you visit a website and you produce some covert traffic for other people who want to visit some other website, for example, WikiLeaks. And the idea is pretty simple. As a user, say, for example, you want to go to Reddit to read some subreddit documents. So you visit Reddit. Reddit gives you a small piece of JavaScript code. And this JavaScript code allows you to create connections to other predefined websites, for example, WikiLeaks. Think about another guy who now also visit Reddit just because to receive some data from WikiLeaks. He's not really into reading some subreddit document. Now we're calling this guy as a active participant. So he's no longer passively contributing to the network, but he's actively getting some data. So what he's communicating is no longer a covert traffic, but active, proper, real traffic. And how do you think about this idea?
Oh, this idea is really cool. You know, when you make the code traffic and the real traffic really looking similar or indistinguishable, then you have, for active participants who wants to access the information on, for in our example, WikiLeaks, has an anonymity set of the size the active and the passive users, which is much more than when just the active users are considered. This mitigates the bootstrapping problem, which we have mentioned before. And because the active participant looks identical like everyone else when he goes to Reddit, even though he wants to get the access information of WikiLeaks, yeah, he gains deniability.
Exactly. So now we know a little bit about the concept of passive participation. So I'll just quickly go through the cover-up primary contribution. So we use the concept of passive participation to create two different types of channels. One is a pure unidirectional channel. We're calling it as the feed. Think feed just like a radio broadcast. So as a radio broadcaster, you really don't know who are the user who are actually listening to your radio broadcast. And then we modify the feed to produce a bidirectional general purpose upload and download channel. We call it as a transfer. We implement both feed and transfer into a fully working prototype. And then, as we already say, that active participants and the passive participants, they are kind of indistinguishable, but later on we'll see that active participants actually use a small piece of software which actually creates some additional timing leakage. This is nothing but some side channel leakage, and we additionally analyze this side channel leakage to understand if our network level adversary can distinguish between active and passive participant or not.
So I'm now going to explain the unidirectional part of cover-up, which we call feed. There are the active and passive participants we have already mentioned before. They are identical, except that the active participants have gained cover-up tool out of band. So the active and passive participants now connect to Reddit. And Reddit includes an iframe in its HTML page that fetches a JavaScript snippet from a server which we call cover-up server. If Reddit and the cover-up server have different domain names, the JavaScript context actually is isolated due to the same origin policy that most modern browsers claim to enforce. Then this JavaScript snippet makes requests to the feed server, in our example WikiLeaks, and this sends the feeds then to active and passive participants. For passive participants, they are now done, but active participants can, with the help of cover-up tool, extract the feed from the browser's cache. For our attacker, we assume that it can monitor and drop network packets, and that it can even fake active and passive participants. He can sit on the entry server, here in this example Reddit, on the cover-up server and the feed server. The only thing that's not allowed to be compromised is the user's machine. This makes sense because when the attacker sits on the user's machine, actually he could anyway see what he is doing. And because for a network layer attacker, the protocols of the passive and active participants are clearly indistinguishable, the protocol-wise, the only difference being cover-up tool at the active participant side. This system provides deniability for people who actually want to visit WikiLeaks.
Now, of course, one of the interesting part is how do we protect the passive participant, because both active and passive participants are completely indistinguishable. So the passive participants also end up getting some data from WikiLeaks, and you really don't want your computer to have some data from some random strange website, right? To understand that how cover-up actually gives the protection mechanism for the passive participant, we have to understand how we distribute these packets. So there is the feed server, and irrespective of whether you are a passive participant or active participant, you're going to have the browser, using which you visit Reddit and get the JavaScript snippet. And additional to the browser, you have your local cache storage, where browser keeps the data permanently on the local disk. So this is your passive participant, and the difference between active and passive participant is the cover-up tool. And what happens is that in the feed server, we keep the data. So for example, the WikiLeaks data into different chunks, and all of these packet chunks are of constant size. When the JavaScript snippet asks for this chunk, the feed server send one of such chunk to the JavaScript. The JavaScript snippet keep it to the local storage. It is very important that the JavaScript only keeps one packet chunk at a time into the local storage by overwriting the previous one. The cover-up tool runs on the background on active participant machine, and it periodically fetches new data. And whenever there is a threshold amount of such chunk, it can reconstruct the entire data in a meaningful way. We are using error correcting code that is called fountain code to provide such chunks. As this is an error correcting code, so we are pretty much resilient to any network packet drop or corruption of packet. And another nice feature about fountain code is that order is not really important. So feed server really doesn't care that which participant are receiving which packet, and that kind of gives the unidirectional property for the feed server. As you remember, I said that it is very important that at a time the JavaScript only keeps one packet into the local storage, because we are using the all or nothing encryption scheme. So until and unless you have threshold amount of such packet, you cannot decrypt them. So one packet is not enough, and this is indistinguishable from a random looking packet because this is encrypted. So that's how we are protecting the passive participants.
Now we said we have a bidirectional channel as well. Previously we have talked about the unidirectional feed. I'm now going to talk about the bidirectional cover-up transfer system, which is very similar to feed. In fact, we have now not anymore a feed server, we call it transfer server because it has additional properties. But we have the passive participants as before, and here active participants. The major difference to the unidirectional feed is that the users have to install a browser extension. Now, if a user wants to make a custom request to the transfer server, this has to be forged by the cover-up tool, sent to the extension using native messaging. This injects it into the JavaScript snippet, which already has been loaded from the cover-up server. This makes the request to the transfer server, but now the data is custom. It would be distinguishable for a network layer attacker, so we use TLS actually to make it looking indistinguishable. Of course, we have everything constant size and so on. And the same thing we do on the way back. This gives us the indistinguishability property, which we already had in the feed before. Now, the JavaScript thing puts information to local storage, and it's assembled by cover-up tool. The difference now is that we have to trust the transfer server, because obviously he knows who is active and who is passive participant. Moreover, we trust the cover-up server, because we need to trust the JavaScript snippet that's running on the user's machine, and if we would check that byte by byte when it's loaded, we would induce a lot of timing leakage, which we are going to talk later about. We want to avoid that, so we trust the cover-up server. We want to put emphasis on that this system augments the feed. It can run in parallel. If the feed uses TLS as well, they are indistinguishable, feed and transfer.
Now we have seen the feed and transfer. Now we want to make sure that these are actually giving indistinguishability guarantee. That is the main contribution for cover-up. So as we have seen from the protocol transcript point of view, active and passive participants are completely identical. They always execute the same job. But only difference between them is that active participant now have the extension and the tool. And it turns out to be when you install this extension and tool on your browser and the operating system, it introduces some small delay into your browser. And that kind of affects the operating system to introduce few microseconds of delay into the packet dispatch. Attacker who is sitting on the network, if he has a mean to resolve this time very highly precision way, he could see these small delays and he could assert that whether you have a certain application or not, and that kind of violates the main deniability guarantee for cover-up. So of course, to understand this more in detail, we evaluate cover-up and we try to understand how much leakage the tool and the extension going to have. And we propose some mitigation technique to reduce the capability of the attacker to distinguish the active and the passive participant. To understand the timing leakage, we set up the experiment completely in LAN environment. We use some high speed switches to eliminate any network induced time. We implement transfer feed and the entry server. We kind of tested both the feed and transfer scenario. And there are two types of timing leakage. Let me tell you how. So first time you go to the feed server and receive the JavaScript snippet, it started making the HTTP request to the transfer server. And when you load the JavaScript, it also loads and activates the context page for the browser extension. So the first time the browser extension gets loaded and the first time it receives a packet from the transfer server, we call this as the loading time. And the subsequent times are called periodic time, and loading time is little bit longer than the periodic time because it involves the loading of the browser extension for the first time. And this is kind of visible from the network attacker point of view. As we are assuming a very strong attacker, he can isolate all the other running processes from the browser. To emulate that, we make sure that there is no other processes running, only the browser is running. And of course, he can resolve all this network timing very precisely. We took around 3 million measurements span over 2 months, and in these 2 months we made sure the active user is running all the time, so which is kind of a worst case situation for us. And this is the timing leakage we receive. So these two histograms that you are seeing corresponding to loading and periodic, the red and the blue line represent active and the passive participants respectively. You can see there has been a significant amount of overlap, but by visually you can see there is a tiny amount of gap between these two histograms that the attacker can use to distinguish between the active and the passive participants.
So as Aritra already said, it's clearly visible by eye that these distributions, these histograms, are different. And because the attacker is not only measure one measurement, one timestamp, but many, many thousands, because the system that runs over a long time, it's quite easy for him to distinguish active participant and a passive participant. It's important to mention actually that we consider the active participant to be active all the time. So this is worst case. He always is interested in the content of WikiLeaks. So what we do to mitigate this problem, we noise this patch time for the request with truncated Gaussian noise. So assume you have these distributions you have seen before, red for the active participant and blue for the passive. They have little overlap, so easy to distinguish. We add Gaussian noise, which is convolution with the noise, and this increases the overlap of these two distributions significantly. This means it's much harder to distinguish active and passive participants. We did this and assumed continual observations for half a year, where we spent 5 hours on the entry server, that means on Reddit. These are the periodic observations Aritra has mentioned before. And we assume that you visit within these 5 hours 50 times the entry server. These are the loading measurements where you initialize the JavaScript. So the results are here. On the x-axis, you see the average delay that we add to each request. This corresponds to the width of the noise that we add. And on the y-axis, you see the attacker's advantage. There, a 0 means that active and passive participants are completely indistinguishable for a network layer attacker, and a 1 means broken arm, so distinguishable. Our results show that for 60 seconds, please see that it's log axis on both axes. And for 60 seconds already, we get an attacker's advantage of 1 out of 1,000. So the possibility to distinguish these active and passive participants is really small. And our measurement assumptions that there are no other processing running on the system are very strong. When you have any other processes running, the whole distributions are much more noised, and it's much more difficult to distinguish active and passive participants.
So we implemented both the cover-up server feed and the tool. For the tool, we implement completely in Java. For the transfer, we consider 2 different use cases. One is interactive browsing, another is chat. So you can browse or chat in a very deniable way. As you can see, the browsing works pretty well because we can retrieve a Pikachu page from the Wikipedia. Just to be precise, we can see other Pokemon pages too, not only Pikachu. And for the browser extension, we use Chrome Web Extension API. For feed, transfer, and cover-up servers are implemented using Servlet API, which are hosted on Tomcat web server. So all the tools are all freely available for download and testing at coverup.atz.ch. For the performance, it's heavily dependent on what is the packet size and what is the frequency, because it's completely parameterized based on the user preference. So given 75 kilobyte of packet size and 60-second frequency, you get good put around 10 kilobit per second, which is enough to download some textual data. Per user overhead is around 22 megabyte per day, which is, in our opinion, is really small, given the other well-known page like CNN or Amazon provides around 5 megabyte per pages. So this is significantly small overhead. Okay, we shouldn't actually have put Google because it's really small. This is just to give an example. So all of these gives you a really good privacy guarantee less than 10 to the minus 3. So this is half a year of measurement, completely unnoised data and continuous usage. So in the real world, you will get this kind of privacy guarantee for years. So if we summarize cover-up, we provide the new concept of passive participation that provides deniability guarantee and increase the anonymity set for websites, for example, WikiLeaks. We implement cover-up and we did the experiment, and we understand what is the timing leakage that could be apparent from such kind of protocols, and we give mitigation techniques to remove these noises. All the measurements, all the data traces and tools are available in GitHub and also coverup.atz.ch, so you should check it out. Thanks for your attention. That's all. Thank you.
Hi, Danny from Princeton. Thank you very much for the interesting system design. So I think I have a question that is, what's the incentive for Reddit to deploy this kind of system? Because apparently the passive user will have more overhead. So why Reddit will let the website do this for everyone?
So the overhead for Reddit itself is very small. It's just one iframe tag.
Yeah.
Yeah.
It's more like Reddit user, the regular user
Yeah.
will become a passive user and have this overhead. So Reddit is slowing down its regular users in some way. So what's the incentive here?
Well, rationally, none. But there are many projects on the internet, like Wikipedia, that run out of goodwill. And this might be such an example too. We discussed the topic of opting in, opting out, ethical issues, and even liability. We have 1.5 pages in the appendix written by a lawyer about liability for web services. Exactly this topic. If you're interested, please read the paper. It's even more graphs in it, so it's nice.
Thank you.
Hello, Matt Johnson from the University of Washington. I had a similar question about ethics that you just answered, but you're looking at me. So I was wondering actually if you could talk a little bit about the thought process behind having users not opt in.
Yeah, this is a difficult issue. Usually, like marketing, a lot of depends on phrasing. So like you notice when you visit a website, yeah, we are using cookies. Then, yeah, well, you cannot click no. But when you phrase it in the right way, or if you are honest to them and say you actually help users maybe from other countries which have issues accessing certain kinds of information, people out of goodwill will opt in, we hope. But we do not have a user study. That's future work.
Hi, John Howell from VMware Research. One question I have is, if I understood you correctly, you're assuming the Reddit in this example is honest but curious, and it always sends the right JavaScript, and you want to be careful not to look at it. One concern I have is that seems like a tender place for the attacker. Like if I'm the government, the agency, and I suspect somebody, then I can cooperate with the honest but curious server and make them honest but not dishonest. And curious, and now I can probe individual people and see if those people are active participants by fiddling with their JavaScript, and nobody who's auditing can tell because those probes are only going to the victims. So can you speak to whether you is there something else we can do there? Or kind of what was the trade-off that made you end up in that spot in your design decision?
That's an interesting question. Actually, we have put the JavaScript delivering on a device we call Core Server. For the feed, actually, it doesn't matter if it's compromised, because all that the JavaScript does is putting the content in a browser's cache, local storage, which is a permanent storage on disk where we read it actually out. Of course, it can do a lot of profiling things. We are not considering this, but this is then the same argument. It's very noisy, everything on operating systems, and we don't think that you can read out much there. For the bi-directional case, the transfer, there it's indeed an issue. That's the first reason that its own server on its own domain are the separated JavaScript contexts by the same origin policy that modern browsers claim to enforce. So that means that Reddit cannot see what's happening in the JavaScript loaded by the Core server. We, in the transfer case, trust the Core server that it's actually delivering the correct JavaScript, because the alternative would be that the browser extension checks the JavaScript byte by byte when it's loaded. The second way induces a lot of timing leakage. We have measured that, and so we decided to trust it, but technically you could check it as well, and then you would remove this constraint.
Thank you.
Okay, one last question. And maybe I should go read your appendix. I'm not a lawyer, obviously not. So I'm trying to understand this notion of deniability, right? So what stops some government from knocking on my door and saying, I want to see your laptop, what chunks are in your laptop, and so on? And why am I, as a passive user, should not be worried about the law coming for me? I guess maybe this is... Yeah.
So for the passive users, there are so many passive users that we assume the government will not really or let's say agencies, not government, agencies do not care for the passive users due to their huge amount. For active users, actually to knock on someone's door is a much higher level of intrusion than just looking at network traffic. Because I don't want to get political. People are more aware when someone comes to your flat than when just they are tapping your internet connection.
Okay, let's thank the speakers once more.